Okay, good morning and welcome to this lecture number 4 in Computer Algebra Systems Summer 2025. So I've already met a lot of problems today not related to this lecture, but now since due to these problems, this is now going to become a completely, what we call a PowerPoint karaoke. So let me see whether I remember what we are going to talk about today. So according to the title on the slide, we are talking about the Runge Kutta methods that you should already be familiar with. Now, this is more a lecture on how to use Mathematica in order to derive to actually derive numerical methods. So what Mathematica in practice is usually used for is not so much to do the actual computations, even though the company of course wants you to do this and tries to convince you that this is a good idea, but what is actually practically done for is that you derive the particular equations that you need to solve, and then you translate them to a different programming language like Fortran or C, and then you export them and apply this in a real programming language that will also execute much faster. Yeah. So because deriving numerical methods requires a lot of algebra. Okay, let's go through this. So there is something I've always have to start. So there's always something that one particular professor has one particular favorite slide, and this is probably my favorite slide, so that you may see in all possible lectures of me. So you may have seen it already, I don't know. We are talking about numerical methods. What does this in general mean? So a numerical method is you apply numerical methods because you want to solve a problem which you cannot solve. Yeah? And this problem that you cannot solve is here indicated by f of x. So what you want to know is there is some function that you want to evaluate for some input x, and you are not able to do this. Yeah, because the solution of this is not known. So that would, for example, be like you have the Navier-Stokes equation, yeah, and you want to know the velocity field at this point to this time, yeah. So and then your problem is the Navier-Stokes equation does not have a known general solution. And it's not even known whether it has solutions, but there's other problems, so you cannot solve this. So since you cannot solve this problem f, you replace this problem f by a problem phi that you evaluate for the same input plus one additional so-called smallness parameter. It could also be several smallness parameters, but you try to have only one smallness parameter usually. Yeah, and now you say that this phi of x gives you the solution f of x plus an error, yeah, which you could recognize that this would always be true, because you can write it the other way around, that I mean the error can have, so the error is unknown, yeah, so if this is a number and this is a number, so that you can give a different they give a different number. So, for example, there is this childish game where as an answer you always give 8. Yeah. So your model is your answer 8, and so you get questions, and sometimes 8 is correct, and 8 may be wrong. Obviously in most cases. So then the error is, so to speak, not controllable. Yeah. So you also need some limit on the error, and this limit on the error is given by this epsilon here, yeah, which is the smallness parameter, which is something that controls the error in that way that if epsilon, so such that there is a limit, that if epsilon goes to 0, this phi x of epsilon is equal to f of x, which means that the error is a function of epsilon, and it has to approach 0 if epsilon goes to 0. Yeah? So in this case, you can write the error in, not always, but so this is our assumption that we make up front, and later we have to check whether this is still true. Yeah, so we make the assumption that we can write the error in terms of a series expansion. Yeah, where we have a series expansion in this epsilon. So we have a sum over constants, error times en times epsilon by the power of n. And the important thing here is that en, so these are constants, they are not allowed to depend on epsilon. Yeah? So you can, so all the dependence of epsilon is within this series expansion, within this epsilon by the power of n. Yeah? So that's completely general, it is a starting point that we use to derive any numerical methods, whether it being control volume, finite elements, or lattice Boltzmann. Yeah, they all rely on this concept, and today we'll apply this to the Runge-Kutta method. So, Runge-Kutta method is of course a method for solving, in principle, ordinary differential equation, but they can also be applied to partial differential equations, just that the partial part has to be solved by different means. Yeah? So it is a time integrator, only in one variable. So, and in principle, these are a class of methods that solve this. I hate this mouse. That solve this sort of problem where we have a time derivative of a dependent variable y. So it's dependent on t, and this is given as a function of y and t, where this function is not a function of any derivatives of y. Yeah? So, and then there is, say, a scheme how this is done, and I hope that you, because you're advanced, you should have learned this already. That now this is being solved through so-called auxiliary variables that we call k1 till ks, where you have parameters with two indices, a, mi, two indices, ci and bi. the other two with just one index, yeah, and where you compute this km as an evaluation of this function f at a starting point yn, which is usually the last time step that you were looking at, yeah, plus your time step delta t and the sum over this coefficients ami times ki. Yeah? So, and this also including progression in time. So n delta t means, okay, for the sake of simplicity, we assume that the time step is constant. Yeah. So doesn't necessarily, it's not necessarily the case, but here is assumed. And there is this other parameter cm. So this cm is basically the increment, the partial increment in time. Yeah. So this will usually be a number smaller or equal than 1. And yes, and then you compute your next time step yn plus 1 as the current time step plus delta t bi and ki. So you see this ki, because this is the evaluation of f, which is a time derivative. This basically gives you a slope. Yeah. So a slope at so if these this AMI are all 0, yeah, so it gives you the slope on the last time step. And what you do here is you progress a little bit and you compute more slopes, usually in between the last time step and the new time steps, and then you do something, you have a weighted sum of the slopes that you computed in order to get to the next time step. That's what Runge Kutta does. So there are, you see, there are a few constraints on this. So what Cm is basically the fraction of the time step at which you compute the slope, yeah, and this also implies that this mi, yeah, sum up to Cm, and because this bi, this here is a weighted sum, the bi also have to sum to 1, yeah. It is not actually written here, but okay. Okay, now the task now is, so we set up this method, and now the task is to find these parameters, yeah, that solve actually our problem. And for this, we now use the Taylor expansion of the solution of this ordinary differential equation. So since I didn't have any time to prepare this, I actually have to read my slides. So okay, we solve this, and the idea is the Runge Kutta method obtains the solution yn plus 1, yeah, so which is y at t plus delta t somehow, given the solution of the previous time step, yeah, so okay, so these are all approximations because they are numeric, yeah, so they include the error. Yn is y of t if the solution of the ODE can be Taylor expanded, which we assume here we can express the solution at a new time step by the Taylor expansion at the development point t. I mean, it is hopefully Taylor expandable because it's a differential equation, so it depends on being continuous, right? So therefore we should be able to Taylor expand this. So Taylor expansion, what do? We want to evaluate y at the position t plus delta t, which is y of t plus the rest of the Taylor expansion, right? So this means we have to take, Taylor expansion. You should know the equation for Taylor expansion is one of the most important tool in the toolkit of numerics guy, yeah, or girl, and delta t by the power of n by n factorial, and so sum over this, and you take the nth derivative. So this is how you would write this in Mathematica, as a total derivative in this case. Yeah, so the nth derivative of y. Okay, so very, very general. Now we now use our knowledge on the ordinary differential equation, because we know that the first time derivative of y is this function f. Yeah, so this is the sort of equation that we can solve for. So what this means, if we subtract one derivative, yeah, I mean here we have the, for example, the second, the third, and the fourth derivative of u, and now we can subtract one time derivative and get the first, the second, and the third derivative of f instead. Yeah, so we take one here away, and then we have this of f. Yeah, because we are using f of y of t, and is the same as this time derivative. So now we are doing numerics, and this means we are truncating our Taylor expansion somewhere, yeah, and assume that the rest is small. So meaning that our smallness parameter obviously is here delta t. Yeah, and this can be, I guess I have to execute these things. So I can define here this Taylor expansion, ys, t, delta t, and m. So I'll go to particular order with my Taylor expansion. It does not go to infinity, and I simply write this equation here. So I said this delta t is my smallness parameter here, and I go with my sum from n from 1 to m. And what I'm going to do then is to take this derivative dt y and t and replace it with f, y, and t, right? And why do I do this twice? Yeah. Okay, so I do. Okay. Yes. So I do this. Okay, I need to do it this way, which so you could imagine that this here would be enough, right? When this starts here from 1, but unfortunately when it starts from 1, I think that Mathematica just doesn't put here 1, it puts the simpler version. Yeah. For that reason, I do this twice. Yeah. So first I replace the first derivative, and then I replace all the further derivatives with one derivative less. Okay, and then I can execute this for different lengths. For example, very obviously I should, when I do this for 1, I get this first order, I get yt. Okay, it's confusing for me that yt is in the back. Mathematica has this tendency to put things in alphabetic order, and this is why it's pretty far. So this is why it writes it for human in an unnatural way, you could say. Yeah. So doing this twice, will give you this delta t, 1/2 delta t square. Yeah. So this is, by the way, this is the right. So this is the way it writes these derivatives, because it now, you know, for even though we are talking about ordinary differential equations, there's an important detail that we have to take into account also in the derivation. Namely that this f, the function f, has two independent variables. Yeah? It has y and t as independent variables. Now this is kind of a problem, yeah, as we will see later, because this is not the same as in the ODE. The ODE has only one. I mean, this is how it's defined. It has only one independent variable, but this f here has two independent variables. And this you see actually showing up in this place, because you see that here comes the first derivative of f in y. Yeah? Okay, so this may come as a surprise, because you may not have expected this, but this is very important to understand the derivation of the Runge-Kutta method. Okay, here we have the derivative with y. Okay, Taylor expansion, expanding the Runge-Kutta method. In the next step, we have to Taylor expand the numerical method with the unspecified parameters. This can only be done with algebra, yeah, because it's an algebraic function. Yeah, we start from our auxiliary variables. So our auxiliary variables Km, you see, is this kind of function here. So this means we have, so what does this mean? Now we actually have, again, two dependent variables, namely y and t. And the thing is, we have here a relatively complicated smallness parameter, yeah? Because our starting point is yn, and then we move by delta t times sum over I equal 1 to s over am and I ki, right? So now this is your offset. This is your smallness parameter in this Taylor expansion in this direction. And here we start with n delta t. This is our starting point, and we move cm delta t. So that means you get a two-dimensional Taylor expansion now. Yeah, one in y and one in t. So reflected by these two sums over jy and jt and factorial and jy factorial, and these here are our steps, yeah, delta t and the sum over blah blah, and here delta t, and okay, here should be cm. So is this a mistake?
Probably you can get a relation.
Yes, okay, because we said previously that cm is the sum over am, right? So this is correct. Maybe it's not beautifully written. Yeah. Okay. So they are expansions in t and y. Yeah, because in this auxiliary variable, y is an independent function, an independent variable. Yeah, so this is the problem with numerics. We turn an independent variable into a dependent variable, a dependent variable into an independent variable. So now we can do this here. So you see, because I've already introduced this stuff here, even though I did not write it. We do not need the Cm, yeah, because the Cm just comes from the A. The Cm comes from the A. So we can write this sum here, this double sum here down. You see, we'll have to take this entire thing by this power as is usual. And yeah, so it's the same equation as above. Yeah, now you can again write this like this, so we can start here with, okay, so obviously I have to execute it. So, if we go first order, then you see, okay, so the way I implemented it is not, that's kind of a little bit interesting, yeah? So the way I implemented it is not that it gives us the first order result, but I go one step in each direction, yeah? Such that you see we get first fyt obviously, then we go one step in the t direction and one step in the y direction, and then we also go one step in each, yeah, because we do both the sums. So then from a numerical, so we need to be careful, yeah, where we truncate this, so it's not so complicated in 2D, but here we have a delta t square, but this doesn't mean that this is an expansion to second order, because you would have, so if you go here actually 2 steps, you will recognize that there is, say, where is it here? Yeah, so you also get a second order just by expanding t. Yeah, so this is, you know, from one perspective, so you go, okay, I don't know whether I actually have to draw this down, but you know, you are kind of like in a matrix, yeah, in a 2-dimensional way where you go all the way to order m in one direction and all the way to order m in the other direction, yeah, and then you could put everything into this square of terms, yeah, but the ones that are down the diagonal, they are of course of the order m square, yeah, but you're not going to m square in this direction, yeah. So this means if you could implement this in a different way that you get the correct order, but then you would get something like approximately a circle in this space. Yeah? So you would have to go to m square and then delete all of them that have higher order. That would be the correct way of doing it. Okay, let me change this back. What I'm doing, yeah. Okay, so in the next step we want to match the Taylor expansion solution of the ODE with the Runge Kutta method. Let us see. Okay, right, so we need to be when we want to match things, then we need to be a little bit more specific, yeah. So say what we are doing is we specify that we have a two-stage Runge-Kutta method, so where there's a parameter, there are two a parameters, and we call this K11, and then we do the expansion of this. So K11, K12, am I in the way? Maybe you just take the other seat. We have lots of space. Okay, so that's the ugly expansion. You see, I'm going far enough with going to first order, I guess, yeah? And here we have the ugly expansion of the other guy, which of course looks the same. It's just a just the name of the parameters are different. And here I don't show it by setting the semicolon. So, okay, what problem do we have? The problem we have is that we have K on the right-hand side of the definition of what I now call KK. Now, as I told you in our exercises, we need to be very, very careful with defining variables. Yeah. So, I mean, from an equation point of view, this is you could say this is not correct. Yeah, I could demonstrate this, but if I demonstrate this, I have to kill the kernel, and because I'm messing things completely up by doing this. Yeah. So because I could define here K1 is equal to this, then it would encounter K1 in its own definition, and then it would try to put K1 into this, and then it goes into, a recursive loop. Yeah, this is why you need to be very careful and not call this thing K1. This is why I called it KK1. Even though I know, Mathematica does not know, but I know that these are the same things. Okay? Because now we have a problem. So K1 depends on K1 and also depends on K2, right? So this is an implicit function. And there are indeed so-called implicit Runge-Kutta methods that make use of exactly this, but they cannot be solved directly. They need to be solved in an iterative way. So you need additional methods to solve this. So the so-called explicit Runge-Kutta methods, that are the ones that you usually learn in your undergraduate class, they have the property that by definition everything that where the second index, where the first index is smaller or equal to the second index, is set to 0. Yeah? So, because if this is the case, you'll see smaller, I said smaller or equal, yeah, so this will drop out. So actually here they all will drop out, yeah, because they will all, A11 and A12 are all 0, that they will all drop out. So all of this will disappear, yeah, but not in this one here, because here we have some that do not disappear. Let me see whether I have this on the next equation, the next slide. Yes. So. Okay, this is now my point. I define a new KK1 is KK, and did I execute all of this? I hope I executed. Maybe I did not execute that one. Yes. So I define a KKK1, dangerous word, Ku Klux Klan. Yeah. Okay, sorry for that. KKK1, KK is KK1 where I replace all this, here use of patterns. Hope you learned this, yeah. A index I and j, so if the index j is larger or equal to I, then it's 0, or otherwise it remains Aij, and I'm actually repeating this until we are done, and then I will, yes, so in addition I will replace k by kk. You see, here we make use of the way Mathematica treats indices. Yeah, so because this is not just a different name, it's not the name KKK1, but the index is something that Mathematica distinguishes. Here, so for example, let me so we have set, no, not that one, set I, yeah? Set I, and I replace set by h. Yeah, so we get hi, right? So this is what you can do with Mathematica. So here I do not need to specify that I want to replace K1 by KK1 and K2 by KK2. Yeah, I could also do this way, but here I replace K by just K by KK. So the meaning of this is, as you see, here we have the K's, and I will plug this here, I will plug this definition into this here, after, that's important, after I removed the this A11, yeah, because J and I would be equal, larger or equal to 0, right? So if I do this, all of this for the first one, because they, as I said, they are all 0, yeah, so they all disappear, right? And for K2, you got a lot left. However, all you are left with is, in the end, A21. Yeah, so they are all, I guess they are all here. Let me see. We could, so KKK, just made this KKK3. No, 2. So what we could do is could collect this, and we are having wrong place. So we can separate out to 1. Let us see. Okay, it does it a little bit ugly, yeah, but they are still okay. So, right. So we get what we observe is we have this here just once, then we have the square of it, we have the third order of it, fourth order, sixth order, and seventh order. Yeah, but remember these are not I mean, the seventh order is not complete in here, yeah, because of what I told you about our expansion. Okay, I'm going to delete this here again. So, now this only is the Taylor expansion of our auxiliary variables. What we want to know is the solution of our method. And the solution of our method is this, solution of our method is actually y of t plus delta t, the sum over bi times kk, yeah, I and this. In this case, because there are only two of them, this is from 1 to 2, right? So this is what comes out. And let me see whether we can make this visible. No. So this is the solution of the Runge-Kutta method. Yeah, of the next step according to the Runge-Kutta method. Yeah, and this next step according to the Runge-Kutta method is now supposed to be the same as the expansion that we had previously. So we made this expansion, sorry, going back. So the expansion of the ordinary differential equation. He has no numerics in it. Yeah. So they have to match. Now we make them match. We make them match. Here, we are here, where we say that, okay, we get this, so we have one as m and the other one y as, okay, yeah, so, yes, so we evaluate our ordinary differential equation and put this into the variable yr, right? So now we have yr and we have ym. So yr comes from, I don't know why I put it this way, the name's this way, but yr comes from the ordinary differential equation and ym comes from the Runge-Kutta method. And what, again, did I do? Okay, it's the mouse. So, as you may have already noticed, this looks a little bit shorter. Yeah, so they are not exactly the same. So, one thing extremely important to all things numerics is equating coefficients, because what you do with equating coefficients is you are turning a series into a sequence. Yeah? So you have the series expansion of both your Runge-Kutta method and your ordinary differential equation, and what you want to have is a sequence of the actual solution and the increasing error terms. Yeah? So, and for this we're using the technique of equating coefficients. So this is very, very basic and very, very important. Okay, since I'm completely unprepared, I still have to read my slides. In order to match both solutions, we have to be aware that the derivative f of y and t are all independent, at least if our method is supposed to be general to all ODEs. So we need to partition the solution according to these independent variables and solve for each of them separately. Yeah, so this is exactly what we do by equating coefficients. We start with recomputing with computing the residuum with the difference between the numerical and the desired solution. Okay, so what we can do is here we subtract these two things and then we say this guy should be 0, right? So the residuum is a polynomial in the derivatives of fyt, we can use Mathematica to separate the coefficients with the polynomial. You just have seen me using this what was it? No, you see me. You saw me using this collect function, yeah, where I could collect the different parts in delta t. So what I'm now, so this is a similar function. Well, let me execute this. This is a similar function where I put all coefficients, make a coefficient list of a polynomial. Yeah. So I get, so I expand this, and then I make a table in, this is again two-dimensional, of all the derivatives. Yeah, of all the derivatives, and now give me a list of all these entries here. So then we get an ugly result. Yeah, so I did not put a semicolon for purpose here, so that you get to see that most of this here is empty, because Mathematica provides a full matrix of all coefficients of possible polynomials. Naturally, most of these are zero, so we tell Mathematica to show only non-zero coefficients, which we can do here by using lambda, by select and using lambda functions. Yeah. So first of all, we flatten. Okay, so what I should potentially say, the derivatives has now disappeared from these things. Yeah, because these are the prefactors of the maybe I should, in order to be less confusing, I should try to get somewhere in between. So let's say coefficient list. Yeah. So say we try to understand the coefficient list. Yeah. So we have a polynomial a plus b times x plus c times x squared. Yeah, that some polynomial.
Coefficient, there's a type at the beginning.
Thank you. So coefficient list. And then we want to have them in, I believe x would be sufficient. Let me see whether this is the case. Okay, something. Okay, I put this in the wrong cell because this is not. This is a text cell. Stupid. I was in the impression that I can get a new cell. No. Okay. Why doesn't this work? Let me try to go to the end.
Maybe above one of the already defined.
What did I already define?
For example, above non-zero coef, that we know that it's a coef.
No, I did not define anything here.
No, I mean, if you try to execute coefficient lists
Yeah.
in one of those and just using a column at the end to...
I don't know whether it's just busy. Okay. The kernel is not reporting. Is not. okay, it was, uh,
So, as I understand this coefficient list is going to return a, for this equation, this quadratic equation, it would return A, B, and C, right? That's the what coefficient list?
yeah,
Okay.
yes.
Okay.
So somehow, okay, I made somehow this all coefficient. Okay, so I see what the problem is. This all coefficient does not return. You see here, this is where we get stuck. I mean, it's just that it may take for ages, or because this is did I change anything critical before that? Okay, I don't know whether this is going to do anything in between. Let me just now suppose this would have had returned. But what we would then do is we'll get this you see it takes a lot of time, yeah, obviously. Then from this big matrix we would flatten that big matrix, and we would select everything that is not zero. So this can be done by this select and using this lambda function. Yeah. So this here. So what's important question for the exam? What does this triple equal sign mean?
Well, I just saw that it's same.
The same. Okay, so what does it mean to be the same?
That if this is evaluated, or
Yeah.
the function that it's evaluated has to be equal to 0, right?
Yeah, but then there is two signs which is also equal to 0, right?
But probably it's definition from the lambda, or it's like the syntax if you...
By the way, this somehow has returned, apparently, because now we got to this here. It's just now taking, this guy is now taking its time. Which is surprising, because there's not that much to do in this. Okay, again.
I was trying
So what is the difference between 2 equal signs and 3 equal signs?
I think it's the first
Okay, so it's a good thing that I have this question, because now it goes on. Yeah. So yes, as you see, you were right. So we get A, B, C. Yeah. So these are the coefficients. I want to take this away again. There is a difference between lazy and eager. Between these things.
Okay.
Yeah, so 2 equal signs is obviously lazy. Yeah, because okay, let me I mean, this is important to know. It's important to know. This say AA equals to BB. Yeah, so what will this give you?
It would return AA equals BB.
Okay, I'll have a. And what would BB equal AA return? I don't know, but I think something else. Yeah, you're right. So I would have said that it will do its alphabetic thing. No, it does not. So, okay. I hate this mouse. Okay. So how could that be different?
Okay, so I think I understand this probably, or I assume that this one is eager, right? So
Yeah.
if we have, because we have one equal for defining a variable.
Yeah. Now we have two of them also, lazy and eager.
Yes, with the.
Yes.
So eager is 1. Lazy is 2 points and equal.
Yeah.
And we also have these two equals for same equation.
Yeah.
But that means that if we wanted to get, it's just, if you get an equation, if you evaluate something, if you want to say that it has to be equal to 0, you need to use an eager.
Yeah, so, or if you want, I mean, if you, is this, I mean, right, so one is you write an equation. So AA in principle could be BB. That's possible, yeah?
Okay.
So, but when we ask, is BBAA, is this the same? Yeah, this is what's the same. No, it's not the same, right?
Okay.
So, because, I mean, very obviously this wouldn't work. I won't repeat it because it takes for ages, as we've seen, yeah? If we ask if this is equal to 0, then all we would get is, you know, these, okay, no, I mean, if it is really 0, 0, 0, then it would actually, it could work, it would work, yes. It would work because we are looking for 0. This is a special case, yeah? Yeah, so it would work because we are specifically looking for 0, yeah? And maybe I use 3 equal signs to squeeze in this question here. Okay, so this, yes, of course, I mean, here this is important that the use of a lambda function is here usually, if we do select, either you would have to define this function first, or what you usually do is here is a lambda function, yeah? So that you don't need to, because you're using it only here, yeah? Okay, so now we go through this order by order. And the thing here, okay, now we did not talk about the other thing. So here we get these coefficients, yeah, and all of them, of course, are still dependent on delta t, on dt in this case, dt, yeah. So, and they appear on this different orders, where I again have to remind you that the higher orders are not correct. Yeah, because they are not complete. Yeah, so but we can say that because we expanded to first order, that they will be at least 2 first order. They will be complete. Yeah. So then, what we are going to do is we select them by order. Yeah. So we take our non-zeros and we set all dt to 0 in order to see whether there's anything left without a dt, right? Okay. Yeah, because this would be very bad. Yeah, because this would mean there would be an error that is not dependent on delta t. So that would render our method inconsistent. It would, you know, I'm going back to the example where your answer is always 8. Yeah? So this would be an answer that is independent that cannot be controlled by a smallness parameter, so it would be inconsistent. So this, in this case, you would have an error of 8. Yeah, that's so. Now here, Runge Kutta is in principle consistent, meaning that for dt equal to 0, we don't get anything. So then, what we do is we go through order by order, and okay, it can be done in different ways. The way I did it here was I say I take order 0, I take my non-zeros, and say that delta t by the power of n, right, is replaced. So if n is larger than, say here, 1, yeah, then we set them to 0. So we let them disappear, or otherwise we set them to dt by the power of n. Yeah, so use this later in order to get to a higher order, and then we select all of them that are non-zero. And what we see is we get out one such term. And this one term includes the condition that I mentioned previously, but which was not written on the slide, namely, but this is, I mean, it comes out of the equation, obviously, namely that b1 and b2, I mean, the sum over b is equal to 1, right? So this is what you can observe here. The sum over b is supposed to be equal to 1, yeah? Because there's b1 and b2, and if their sum is equal to 1, then this will disappear. So, this means you have to, if you still want to determine one, you have to, decide on one. Yeah. So the one that you want to eliminate. So let's say my solution 1, yeah, is to be solved for b1, so that I have to get b2 later, and I can do this by again using lambda functions. It's very seldom that I find Mathematica inconsistent, but in this case, you see, I'm a little bit confused here, because select takes the list and then the function, and map takes the function and then the list. Okay. Yeah. That's the way it is. Yeah. So we use this function when it's equal to, now I put the equal sign here. Because I want to, this is equation, yeah. So there need to be equal sign here, not that one. So I make my equations, and then I solve for b1, please.
If we use three equal signs, it would return false, right?
Yeah, then it would. I mean, the solve would, the solve would tell you this is not. Okay. It doesn't even allow me to write it. Why not?
But in terms just of this, probably only with the map. If we get only the map with 3, it would be, well, it won't allow.
No, it should allow. This was a. So if we just map, yeah, maybe I have to. I think I have to rewrite it. That's the point.
Okay.
So that would give you false, and then solve would tell you that you cannot solve false. Yeah. So. Okay, it doesn't work. Right, so this comes out that b1 must be 1 minus b2, obviously, yeah? So then we go to second order. So we do the same thing, just we say here is in, we replace this 1 by by 2. And okay, so there's one important thing. Okay. Now, how comes if I do this? Okay, question to you. If I now do this again, I would expect that the first order solution, that the first order terms are still in it. Yeah?
Mm-hmm.
So how comes there's only the second order terms here left?
Because if you go to second order.
Okay, look at what I've written. I mean.
Because you use the first order.
Okay, yes, because I take my non-zero coefficients and I replace B1 with this.
Mm-hmm.
And I know that this eliminates all first order terms.
Mm-hmm.
Yeah? So this is why the first order terms are already gone. Okay, now we only get second order terms. And if you look, I mean, this is something now, we are cheating, don't look, usually we let Mathematica do, yeah, and the result is big and ugly and we don't see. Now this result is relatively small than we can still see, and what we see if we look is that there are two equations, obviously, and they put the same condition. Yeah? So this may lead to some trouble because you may think, okay, we have 5 equations, we have 5 variables and we can solve them, but as you see, they don't necessarily, they don't need to be independent of each other. Yeah? So this is a possibility. This is why I say let's be ignorant and try to solve it. Yeah. So because we have now 2 variables that we want to solve for, B2 and A21. Yeah. And if we had 2 equations that would be independent, we could solve for them. And this is not the case because they are obviously dependent. So we are left with this mouse that drives me crazy. Yeah, so we cannot solve this thing. And the reason behind this is actually the... okay, so you would have to have a look again on everything, but the actual reason behind this is that y has become an independent variable. Yeah? So, because, if we had only one-dimensional Taylor expansion, in both cases, so in the ODE we have a one-dimensional Taylor expansion only in time, where in the numerical method we have a two-dimensional Taylor expansion. If we had one-dimensional Taylor expansion in both cases, then adding one parameter more would always give us the possibility to eliminate one term. So we'll always increase one order. Yeah? Here, because we're matching a two-dimensional with a one-dimensional Taylor expansion, we get more easily stuck. Okay. Yeah? This is why we why there is not. I mean, otherwise there would be a unique solution for the next step, and always we could always get just one. We could always subtract just one term. And the problem is now one term in the one expansion with with delta t by n in this expansion corresponds to several terms in the other expansion. So no solution. now human, maybe artificial intelligence can do this for you too, but apparently human has to get thinking again, and we have to make a decision, so we want to solve for one of them. Yeah? So I take one of them out, let's say I take B2 out, and I solve this one equation that I have, and then I get a relation between B2 and A21. Yeah? And unfortunately, in this method, so, which now means we get to this order, we have some choices. Yeah, so we can, at this particular order, put kind of any A here, provided we put the right B and we get a solution at this order. This is the reason why there is many Runge-Kutta methods of second order. Yeah. So what you would usually do is, I mean, in a way you are lucky, yeah? So you used up only one coefficient to clean this order, so you have one left that you could put in the next order. Yeah? But because, see, in a one-dimensional Taylor expansion again, each order would have one term. In a two-dimensional Taylor expansion, each order has several terms, and they become more terms the higher the order. Yeah. So I mean, how many permutations do you have to combine third order with t and y? Yeah. So you'll have t. You have t by the power of 3. You have y t by the power of 2. You have y squared by the power y squared by t, and you have y cubed. Yeah. So you have many terms. So problem is, if you now go to order 3, you get 3 equations here out. And they are now no longer all the same. Let me see. I guess these two are, wait, so these, some of them are compatible. Yeah, so you get lucky. You got lucky with these here, because this is just the same thing multiplied by 2. Yeah. However, there is something very nasty. dt by the cube divided by 6. This does not depend on our parameters. Yeah, so this will not disappear. So they obviously, this is, I mean, it will disappear when you put dt to 0, which of course, then, but it won't disappear otherwise. Okay, so there is no solution. What we can try to do is we can use the reduce, so we cannot solve this. We can use the reduce function in order to reduce this system. That makes us only, okay, that will only show us that we get rid of this stuff only if dt is 0. That's the only way we get. We can reduce this to 0. So otherwise we always have this. So basically it cannot be solved only if the time step is 0, which means that the third order error cannot be eliminated, even though we have not yet determined all parameters. This is the reason why there are different Runge-Kutta methods of second order. But could there still be one which is better than the others? The problem appears that there is one term in order 3 which does not depend on the parameters. Let us eliminate these terms as we cannot do anything about them anyway. So if we eliminate them, okay, so how are we doing this? Order 3b, select order 3. Now here, we again use a lambda function, so we ask for the position of the parameter we are looking for, and if we select it only if the position is a non-empty list. So basically what this means is this is a crazy way of saying, so in this term there need to be an A1, 2.
Okay.
Yeah? So that means that everything that does not contain this will be eliminated, and this is what we are left with. So then we can reduce this again, and if we reduce it, we see that now there are two conditions that put this to 0, namely dt is equal to 0, or A1, 2 is equal to 2/3. Okay? So then we would say our best guess is A21 is equal to 2/3 because it eliminates the largest amount of terms that we have at this order. But this is, mathematically speaking, this is very controversial because we did not improve the method by this. The error is still at the same order. Yeah? So we just said there is a thing, I cannot get rid of this, so I first get rid of everything else. That's the same size. So it is, philosophically speaking, very controversial whether we say that this is a better method than any other choice of A for A21, but in practice it may or may not be a bit better. Okay, so if we put A21 to 2/3, then and we put this into the solution 2, then we get that B2 is 3/4 and B1 is 1/4, which of course when you put them together gives you 1. Okay, now did we discover anything? Do you know this method? Yes, no, did you know the method with where you get these coefficients?
No.
It's the Ralström method.
No.
Yeah, so it's, there's, yeah. Of course, I mean, I also made this as an exercise, and for a different lecture, and notice, oh yeah, you get this with the coefficient, and I was not aware. Of course, you look it up, and this is a pretty easy peasy thing. That is of course this already has a name, yeah. So, but the fun thing is, if you are not aware, you end up with the same thing, yeah. You see how it's derived. So I actually derived this and then looked up what is the name of this method, yeah. Okay, now we go a little bit go to implementation things. So yes, we compute the new time step. We get the function y, f, t. So y would be our variable, f is the function here, t, dt, and of course we need some starting parameter. We have a module, which is scoping device. Yeah, so we have local variables k1, k2, I, and j. We get k1. Okay, yes. So what we imply here is that this y and f actually can be a vector. Yeah, we can work with vectors. Y and f can be vectors. Yeah. So we go through all the components of the vector. I mean, we're assuming that this will be a vector, so and we get this for k1 and k2. And here we set our parameters and then we return. So, I mean, this can be done with a vector, yeah? When y0 is a vector, then we just add this and we get a new vector. So, and now let us apply this in our last few minutes to our, I say, currently favorite epidemiological ODE. So this is aging now a little bit because COVID is getting less common, even though, you know, my mother just had it a few months ago. Yeah, it's still possible. You may remember this, that a few years ago, everybody was solving these very, very simple equations, and maybe also a few more complicated, but this was the starting point. You say that there's a number of people that are susceptible, and some that are infected, and some that are, as we say, removed, because they may either die or they may be recovered. Yeah. So the time change in the number of people, or the fraction of people that can get the disease will decrease in time when there are new infections, and the infection is given by a spreading parameter beta, and times the number of infected people times the number of non-infected people. Yeah, so infected times susceptible, and all of this divided by the population N. So these that are removed, so this is a so-called compartment equation. Yeah, there's a compartment S from which population is removed. The population that is removed from S is added to infected. So who is getting infected enters infection. So there's the same thing here, just with a plus. And then there is a removal, because people being infected can be removed from being infected by either dying or by getting well again. Yeah. So this is this gamma, which is only dependent on the number of infected people, and this will add to the removed. Now you can plug this, you know. So this was just a new time step. Now you write this to, you know, a list of solutions. So we have this. Where do I actually have the equations? Okay, now yes, we still give the equation in this here, but we have 3 different outputs, and this is a list where we append the new result together with, so the first entrance is the time, I times dt, and the second is the output, and then we'll give 3 different equations, okay? So, and we put our equations here. So we say now SIR result 1 day, so we integrate over 1 day. Okay, I have to write I with 2I. Why do I do this?
Because otherwise it would.
No, because I is the imaginary unit. So there are a few things that you cannot use. So you cannot use I, you cannot use E, and you cannot use N.
But is it capital?
In capital,
okay.
yes. Yeah. So I need to call it I because I would be the imaginary unit in Mathematica. So this is why I call it this way, and then I specify my equations here. I set some parameters. So this is the number of people in, say, Germany. I'm a little bit self-centered here. And t is the variable, and the length of the time step is 1. And then I go. So I set this, the number of susceptible people to 80 million, and I take the infected to 10. And then I do everything for 300 days. So then we can also run this for 10 days, and here we get slightly different solutions. Yeah, so this is the one that, you see, we get it in points. I left it with points that you see how many points. So each day is 1 point. Yeah, so it will behave like this, and here we have the one for 10 days, and you see this is a very simple differential equation which comes with a relatively stable solution. So I think that the result down here, the number of susceptible, yeah, is not quite so accurate. Yeah, so there are more left here than here. I guess. Let me see whether I have on the next. Yeah, okay, so we can compare this method to the more common so-called half-step methods, where we say that A12 is equal to 1, B1 is 0, and B2 is 1. Yeah, that's what a method that is more common than to use this 1/3. Yeah, it has the same order of accuracy, but our method, apparently, because we deleted some other parts, should still have a better accuracy. So we can run this. I would say the results look pretty similar. So you see, order is important, yeah? Because I don't even see the blue one here, but I see red and orange. Red and orange. Yeah, you see there is this big offset. Okay, in terms of when the time step is very large, the orange, because obviously the 1 day must be more accurate, and for the 1 day, both methods agree very, very well. Yeah. So other than that, the orange is a little bit better than the red. Yeah, almost negligible, but just a little bit better than the red one, which means that for this particular case, actually, the new method is just so slightly better than the half-step method. Yeah. Okay. Yes. Running out of time. Thank you for coming, and we see each other next week again. Yeah.